Okay, so part 2 of our video, we're going to look at our first example where we're going to use a goodness of fit test. So, in his book Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. To see if birth date is related to success, judged by whether the player makes it to the NHL, a random sample of 80 NHL players from the 2009-2010 season were selected and their birthdays were recorded. Overall, 32 were born in the first quarter, 20 were born in the second quarter, 16 in the third, and 12 in the fourth. Does the data provide convincing evidence that the birthdays of NHL players are not uniformly distributed throughout the year? So remember, this last sentence is usually telling us what we are trying to show. What we're trying to show is the alternative hypothesis. So we have to think of kind of the opposite of that for the null hypothesis. So if we're trying to show that birthdays are not uniformly distributed throughout the year, we're going to say our null hypothesis is that birthdays are uniformly distributed throughout the year. So I've pre-typed these out. You can pause the video if you need to write it down. But the null hypothesis is birthdays of NHL players are equally distributed in the quarters of the year, meaning that the birthdays are evenly happening throughout the year. And so I've said P1 equals P2 equals P3 equals P4, thinking about these as proportions, and if they're all equal, they'd actually be equal to the 0.25. Every single one of those, 25% of the birthdays should be in the first quarter of the year, 25% of the birthdays should be in the second quarter, and so forth. So if this is what we're assuming with the null hypothesis, our alternative is that birthdays are not equally distributed throughout the quarters of the year. Or in other words, at least one of the PIs is wrong. Remember, PI represents P1, 2, 3, or 4. So if at least one of these is wrong, that's where our alternative says it's not equally distributed. Okay? You'll have to practice writing out your guys' nulls and alternatives. That is something new here. But we're always trying to write the null based on what they're claiming, so that our alternative is kind of usually what they're asking here. Now, with all the 4-step processes, we have the plan where we have to name it. In this case, we have the Chi Square goodness of fit test. We always go through the conditions here. Well, I mentioned the conditions above. The first one that we're always going to have is the random condition. I grabbed this quote out of the sentence above. Random sample of 80 NHL players. We know that it's random. Because we took an SRS, we need to mention the 10% condition. So we are saying that 80 is less than 10% of all NHL players. Now you might be thinking, there's not 800 NHL players, and you're probably right. So we're going to have to use caution a little bit for this one. I guess we could kind of stretch it and say 80 is less than 10% of all NHL players that have ever played. So we do kind of have to stretch that one for it to work. So I'm just going to go ahead and point to that and just say use caution. We're going to keep going. Now, usually the next condition is the normal condition, but because we're not using a normal distribution, we're going to check the large sample size condition. We need to show that all expected counts are greater than or equal to 5. Now, sometimes we're going to show this above. In this case, we haven't shown it yet. We have not yet checked that the expected counts are greater than or equal to 5. So what we're going to have to do is figure out these expected counts. Now remember, there were 84 NHL players. We are expecting their birthdays to be evenly distributed throughout the year. We are expecting 25% of all the birthdays to be in each quarter. So 84 times 0.25 is equal to 20. In other words, we are expecting 20 birthdays in each quarter of the year. Well, guess what? That's greater than or equal to 5. So our expected counts, what we're expecting to see, is greater than or equal to 5. We've met the large sample size condition. All right, now the do portion. This is where we're going to calculate our test statistic and our p-value, just like we've always done. Well, you know how I am. I'm big on pictures. So I'm going to draw my picture, and remember to draw a skewed to the right distribution. That's what your chi-square distribution looks like. And with all chi-square distributions, you need to list your degrees of freedom. Now remember, degrees of freedom is the number of categories minus 1. Well, in this case, we have 4 quarters of the year. So we're going to say 4 minus 1 equals a degrees of freedom of 3. Okay? Now, what we're going to try to do is we're going to try to figure out our test statistic. In our case, our test statistic is chi-squared. What does this chi-squared equal? That's going to tell us the probability of receiving a chi-squared statistic that large or larger. Okay, well, that's how we're going to get our p-value. So I kind of showed you how to figure out chi-squared a little bit yesterday. If you remember, I told you that a chi-squared is figuring out how far apart the observed is from the expected. So we take all of our observed counts, which is from our actual sample, and we subtract it from the expected counts. That's how far off they are. But as you guys are probably familiar with, we normally square those differences because squaring it gets rid of any of those negatives. But because we square it, we have to kind of cancel that out, and the way we do that is by dividing by the expected, since the expecteds are sometimes weighted differently. In this case, because they're all uniformly distributed, we're going to be dividing by the same thing, but that's not always the case for every example. Now this formula only gives one component of chi-squared. In our case, we have multiple components. So what we have to do is after we found all of those components, we add them all together. We find the sum of all of the individual components. So here's what I mean by that. The first quarter of the year, if you look up at our example, the first quarter of the year, 32 were born in the first quarter. So that's my first observed count. 32 minus, we were expecting 20. We're going to square it and divide by the expected of 20. Okay, now looking above, you probably see that there were 20 born in the second quarter. We're going to subtract it by the 20 we were expecting, square it, and divide by 20. In the third quarter, there were 16 birthdays, minus the 20 squared, divided by the 20. And in the fourth quarter, there were 12 birthdays, minus the 20 that we expected, squared, divided by the expected. So I actually have a shortcut to show you guys on the calculators of how to calculate these quickly. So I have figured out how to do this pretty handy. So here's our calculators. I'm just going to show you in one because it's the same in the exact one. But what I would do is I'd go to our lists and I would plug those in. 32, 20, 16, 12. These are our expected, or I'm sorry, these are the observed. This is what we actually saw. Now remember, we were expecting 20 in each quarter because we're expecting that they're evenly distributed. Now remember, we're doing the exact same formula on every single one of these. So all you got to do is scroll up to list 3 and use parentheses. We're going to say list 1 minus list 2, observed minus expected, squared, actually I'm going to use that symbol, and then I'm going to say divided by the expected, which is in list 2. So if you pre-do the formula out and you hit enter, it calculates all of those for you. So the first one is 7.2, 0, 0.8, and 3.2. If I went too fast through that, you can rewind it and rewatch me doing that. But that's a quick way to find all the components, especially if your example has more than 4 expected and observed counts, and you can do it a lot quicker with your calculator this way. So I already calculated all of these out. I'm going to copy them over from my calculator. 7.2 plus 0 plus 0.8 plus 3.2. If you add all of those up, you get your chi-squared statistic of 11.2. Okay, that's how far over we are on the chi-squared distribution. So now I want to know the p-value. What's the probability of getting a chi-squared distribution of 11.2 or greater? Well, we know how to deal with distributions. In fact, this is a different distribution than what we're used to. This is a chi-squared distribution. So hopefully you can guess that we need to go to the distribution area of our calculator, and we're going to select Chi Squared CDF. Remember, the CDF is the combined distributions. And when you do that, you have to, again, type in some values. We should be somewhat used to this. We need to put in a lower bound, we need to put in an upper bound, and we need to put in a degrees of freedom. So in our case, if we look at this picture, we're going to plug in Chi Squared CDF. Our lower bound is our Chi Squared test statistic, 11.2. The upper bound is anything greater than that. Well, that's 999 is what we usually use. And we said earlier that the degrees of freedom is 3. Okay, so I'm going to show you on the calculator what that looks like. All right, I'm going to go ahead and exit out of this. And this is where the calculators are going to look a little different, which is why I have both of them. But if you can see this distribution section on the calculator, that's where we're going to see our chi-squared distribution, or any kind of distribution for that matter. So if you go second distribution, you're going to probably scroll through there. You see option 7 is chi-squared PDF. If you scroll down one more, that's chi-squared CDF. We're going to select that one. But again, if I do the other calculator, option 8, it looks a little bit different. In fact, I already have these all plugged in here. It says lower, upper, degrees of freedom. Okay, so that's what I'm going to type into this one. My lower bound is the 11.2. The upper bound is 999. Degrees of freedom is 3. And when you plug all that into the newer calculator and hit paste, you'll see that that's exactly what they typed in as well. So when I hit enter on both of these, that's the p-value. That's the area under the curve of the chi-squared distribution with those bounds. Okay? So, like my calculator says, I got a p-value of 0.011. That's my p-value. That's this area right here, this black shaded area. So that's the work. We found the test statistic. We found the p-value. That's what we're always doing in the do portion of a 4-step process. So lastly, we go to our conclusion. And our conclusion is written just like all the other conclusions. There might be slight differences here and there, but I think if you guys are familiar with the conclusions, you'll see how those differences go. Assuming the null hypothesis is true, that NHL birthdays are equally distributed, there is a what kind of probability? The p-value, 0.011 probability of obtaining a chi-squared value, because remember, this is where the statistic goes, of obtaining a chi-squared value of 11.2 or, look at the shading, greater, purely by chance. In fact, all the chi-squareds are going to be from here and greater. This provides, well, according to my p-value is small, so this provides strong evidence against the null hypothesis and is statistically significant at alpha equals 0.05. And remember, that's because 0.011 is less than 0.05. Therefore, we reject the null hypothesis and can conclude that NHL birthdays are not equally distributed. So hopefully you guys see some huge similarities within the conclusion. Now, one last piece here is that in the conclusion, because we rejected the null hypothesis, we can actually go further and say not only are they not equally distributed, but we can say why they're not equally distributed. So we often want to do a follow-up analysis when we reject the null hypothesis. So when a chi-squared test statistic gives a p-value that is significant, we must perform a follow-up analysis. To do this, we find the largest component of the chi-squared test statistic. If you guys remember, these numbers right here, these are my components. These are the pieces that helped me create my chi-squared test statistic. And take a look at this one. 7.2. That is the largest component. So that's probably the biggest reason why these birthdays are not evenly distributed. And so that's what we're going to say in a follow-up analysis. So here's what a follow-up analysis looks like. You can continue your conclusion by saying the largest component of chi squared is 7.2 because the first quarter of the year had more birthdays than expected. Remember that we expected 20 birthdays and there were 32 in the first quarter. So that was the largest component, which made chi squared so large, which made my p-value so small, which is why we rejected the null hypothesis. So that is your first chi-squared distribution. I'm going to go ahead and stop the video, and if you want to try the next example, I would give it a shot first, and then you can watch the third video to see how to do example 2.